This time, I'm going to talk about locally linear embedding, or LLE in Python. LLE is one technique for dimensionality reduction. Dimensionality reduction maps the high-dimensional data onto a lower dimensional space in order to reveal meaningful information for their structure. In general, there are two kinds of popular techniques for dimensionality reduction. One is principal component analysis, or PCA. PCA is a linear method. In my YouTube channel, I have another video talking about PCA in detail. If you haven't watched that video yet, you are welcome to watch that PCA video first. Second type of techniques is nonlinear methods, such as MDS, LLE. Those nonlinear methods compute low-dimensional embedding that best preserve pairwise distances. Both methods employ eigenvalue calculations. First, let me clarify two concepts: Euclidean distance and geodesic distance. Think about this manifold. There are 2 points, point A and point B. So, how can we reach point B from point A? One choice is we just draw a straight line from A to B. And this distance, we call it Euclidean distance. But if we have restriction from A to B, for example, we have to move along this manifold. We can't fly over through the space. And then when we draw the shortest line along this manifold, this distance is called geodesic distance. For example, I live in New York. If I want to go to New Jersey by car, I have to go through either George Washington Bridge or Triborough Bridge or Lincoln Tunnel. I can't fly over the Hudson River. That's the restriction. So we have to go through a bridge or tunnel to reach New Jersey. Before talking about LLE, let's talk about Isomap. Isomap is a nonlinear dimensionality reduction method based on the spectral theory, which tries to preserve the geodesic distances in the lower dimension. There are several steps when we use Isomap. First, we will use a KNN approach to find the k nearest neighbors of every data point. And then, once the neighbors are found, construct a neighborhood graph where points are connected to each other if they are each other's neighbors. Remember, we have a parameter k here. This is the restriction. And then the data points that are not neighbors remain unconnected. And third step, we will compute the shortest path between each pair of data points. And lastly, we will use multidimensional scaling, MDS, I mentioned before, to compute lower dimensional embedding. Then, how about locally linear embedding, LLE? LLE is a method of nonlinear dimensionality reduction, which performs nonlinear dimensionality reduction by preserving the neighborhood structure of the data points. This is similar to Isomap. And the basic assumption of LLE is each data point and its neighbor lie on or close to a locally linear patch of the manifold. And the general idea is to present local geometry of the patches by linear coefficients that construct each data point from its neighbors. Let's take a look at this Swiss roll. If we want reconstruct this three-dimensional image to a two-dimensional image, and then we can't say this point is similar to this point because they are closer in space. If we take a look at this image, there's no way we can jump from this point to this point because there's a gap here. Just like my example, it's like there is a Hudson River right here. And then if we want to reach this point to this point, we have to go through the neighbor little by little, and eventually we can reach this point. That's the basic idea of this locally linear embedding. Let's take a look at this LLE process. First, this is the same like Isomap method. We will find the k nearest neighbors. Remember, this k is very critical. If k is chosen to be too small or too large, it will not be able to accommodate the geometry of the original data. Here, you pick k number for your model, and then we'll do a weighted aggregation of the neighbors of each point to construct a new point. For example, for this point, we'll pick up its neighbors and then put a weight here. The weight is W here, and then reconstruct this data point. And rows of the weight matrix must equal to 1. That is, this is restriction. This is our cost function, and we want to minimize the cost function. This is our original data point, and this is our reconstructed data point with all the weight we decided, and we want them to be as close as possible. And the third step, we will go to the new vector space y, and then we minimize the cost for y at the new point. Look at those two formulas. They are very similar, and the most important point is the weight here will be used in this new vector space. We use the same weight. This is very important point of the regular locally linear embedding method. Then, what's the intuition of locally linear embedding? In the original space, there are large d dimensions, and in the new space, we have small d dimensions. And when we perform the transformation, we will use the same weight to reconstruct the data points. when we construct the new space, because we only consider the neighbors of a data point, so it looks like we will take a pair of scissors, cutting out locally linear patches and placing them in the low-dimensional embedding space. In that case, we can think about this small patch as a linear space. We need no more than rotation, translation, and scaling. When the patch arrives at its low-dimensional destination, we expect the same ways to reconstruct each data point from its neighbors. LLE constructs a neighborhood preserving mapping based on the above idea. Until now, I talked about basic LLE or regular LLE. There are many enhancement methodology about LLE. For example, there is a method called Hessian LLE. With Hessian LLE, it will build graph from k nearest neighbors. This is exactly the same with regular LLE. But the next step, it will estimate tangent Hessians. This is different. And then lastly, it will compute embedding based on Hessians. So the basic or regular LLE will calculate the weight based on the distance among those neighbors of the data points. But for Hessians, it focuses on tangent Hessians. Another method is called modified LLE. Remember, in regular LLE, we use same weight for the new space and the existing space. But MLLE will modify or adjust the reconstruction weights. Another enhanced LLE method is called Local Tangent Space Alignment, or LTSA. LTSA computes the tangent space at every point by computing the d-first principal components in each local neighborhood. It then optimizes to find an embedding that align the tangent spaces. LTSA is based on the intuition that when a manifold is correctly unfolded, all the tangent hyperplanes to the manifold will become aligned. It begins by computing the k nearest neighbors of every point. So this is original data point, and then the LTSA will calculate the tangent space and then try to deduct dimensionality with this new method. Now, let's go to Python and try to implement all those methods. This is a Python program. First, we need to import all the library we are going to use, and then we have a function to plot 3D data, and then we have a function to plot 2D data. And this is the core part of this program. It will run the LLE you can specify the number of neighbors and the number of dimensions and what kind of method you want to use. And for the data, I'm going to use regular Swiss roll and modified Swiss roll. I'm going to show you what are those data look like in a minute. And also, for the comparison purpose, I'm going to run Isomap as well. And then here we will run different method. This is standard method, or we call it regular. And then we will use the Hessian method, and then modified LLE, and then LTSA, and then we are going to plot all those graphs to show the result. Let's run the program. And also, I will upload this program to my GitHub, so you can download the source code and run it and see it for yourself. And of course, you can change all those parameters like neighbor numbers to see how it will affect your result. Now the program is running, and after it finishes, it will generate several files in my directory, and then we can see the results. This is regular Swiss roll, so this is our input data. And this one is modified Swiss roll. You can see the regular Swiss roll will go like this, and then this modified Swiss roll has a tail here. And then after we run the LLE, this one is a regular SSE. You can see the result is not that good. And when we try this LLE or Hessian LLE, you can see we got decent result. And if we compare with this original data, it looks like we unroll the data, become like this. And next method, we use modified LLE. You can see basically they look like very similar. And next method, we use LTSA, and if you compare, it's also very similar, very good result. And next one, we use Isomap. You can see all those data points gathered together, not as good as our like LTSA or MLE or HLLE. You can compare. See, obviously the Isomap didn't give us a very good result. And this is all for this regular Swiss roll. And for this modified Swiss roll, I didn't do all the method. I only did this MLE. For this modified Swiss roll, it looked like this. And if we try Isomap, it looked like this. And again, obviously, this MLE give us a better result than this Isomap. After you download my source code, you can add all those methods for this modified Swiss roll and run it and see what you will get. This is how LLE works and how you can implement LLE in Python. Please provide your comments and subscribe to my channel. Thank you very much for watching.